morning all. In today's class, we are going to see about the introduction of flip-flops, types of flip-flops, and the working of each and every flip-flop, and finally the conversion of one flip-flop into another flip-flop. So we have already seen the differences between flip-flops and latches. So flip-flops and latches are 1-bit memory devices. So difference between these latches and flip-flops is that only depends upon the clock signal. So latches does not have a clock signal, whereas the flip-flops will have a clock signal for its operation. Only if the clock signal is provided, only then the flip-flop starts its operation. So flip-flops are 1-bit memory devices that are clocked. So depending upon the clock pulse given, so there are two types of triggering, level and edge triggering. So in level triggering, the output state is allowed to change according to the input when active level is maintained at the enabled input. So we have to maintain the level. There are two types of levels, positive level and negative level. So if it is positive level triggering means the output responds to the input changes only when the clock signal is enabled at a high position, that is 1. Only when the enable input is 1, the level it is called as positive level triggering. Only at that particular time the flip-flops will start its operation. So when coming to the negative level triggered, the output of the flip-flop respond to the input changes only when it is enable input is 0, that is low. So that is called as negative level triggering. So edge triggering means it also involves two types, positive edge triggering and negative edge triggering. So in edge triggering, the output responds to the changes in the input only at the positive edge or at the negative edge of the clock pulse. So if the clock pulse, if the triggering is given at the positive clock pulse, then the flip-flop will respond to the changes only at the positive edges. If it is negative edge triggering means the output respond to the changes in the input only at the negative edge of the clock pulse of the clock input. So these are the types of triggering, level triggering and edge triggering. Level triggering, you have two types, positive level trigger and negative level trigger. So high level, in positive level triggering, only the output will respond only when the level is high. In negative level triggering, the output will respond to the input change only when the level is low, that is 0. So coming to the edge triggering, in edge triggering, the output responds to the input only at positive or negative edge. So depending on the positive or negative edge, you have two types, positive edge triggering and negative edge triggering. So in positive edge triggering, the output will respond to the input change only at the positive edge of the clock pulse. In negative edge triggering, the output will respond to the clock pulse only at the negative edge of the clock pulse of the clock input. So depending upon these triggering and input output values, the flip-flops are classified into 4 basic types, that is SR flip-flop, D flip-flop, T flip-flop and JK flip-flop. So first one is SR flip-flop. So in SR flip-flop, we are going to see about the positive edge triggered SR flip-flop, which means this flip-flop will respond to the input changes only at the positive edge of the clock pulse. So the circuit is similar to the SR latch, except enable signal is circuit is similar to the SR latch, except enable signal is replaced by the clock pulse. So in latches, you have the enable signal. If you have the clock pulse signal, it is called as a flip-flop. So in the figure, you can see that the clock pulse is given to the positive edge detector circuit. The detector will detect only the positive edges will arrive. So only at the positive edges, the flip-flop will start its function. So you have a NAND gates. The SR flip-flop consists of a NAND gates. S denotes the set condition and R denotes the reset condition. So Q and Q bar is the output and the output complement of the output. So this is the truth table for the positive edge triggered clocked SR flip-flop. So in the truth table, you have first column as a clock pulse. So in the clock pulse, you can see that the edges are rising. So rising edge means it denotes the positive edge. So only if positive edge is given, there will be some output. If the clock pulse is 0, whatever the input may be, there is no change in the next state. So whatever may be present state, that is equal to the next state, there will be no change. That denotes that the flip-flop is not in operation when the clock pulse is 0. So only when the clock pulse is positive edge, the flip-flop does its function. So depending upon the inputs given and the present state and next state, we have a truth table for 4 different conditions. So first condition is when set is equal to 0, that is S is equal to 0 and reset equal to 0, that is R is equal to 0. When both S is equal to 0 and R is equal to 0, your present state will be equal to the next state. So Qn denotes the present state, Qn plus 1 denotes the next state. So you can see that in the truth table, when S is equal to 0 and R is equal to 0, there is no change in the states of the flip-flop. So present state is equal to the next state, so that the condition can be defined as no change, that is NC. So after that, the second condition is when S is equal to 0 and R is equal to 1. That means set is equal to 0 and reset is equal to 1. So we are resetting the flip-flop. So automatically what will happen is the next state will reach to 0. Since we are doing the reset operation, whatever may be the present state, the next state will go to the 0, which means reset state. The third condition is S is equal to 1 and R is equal to 0. We are doing S, that means set should be equal to 1 and reset equal to 0. So we are setting the flip-flop. So in this condition, the flip-flop will go to the condition set, so that the next state will become 1. Whatever may be the present state, the next state will become 1. That is called as a set condition. Then fourth condition is S is equal to 1 and R is equal to 1. So if both are 1 in SR flip-flop, we cannot determine the next state of the flip-flop. That is the drawback in the SR flip-flop. So S is equal to 1 and R is equal to 1. When both are 1, we are unable to determine the next state of the flip-flop. So this condition is called as indeterminate condition. So the last two columns, last two rows define that when the clock pulse is 0, whatever may be the S and R, the present state is equal to the next state, that is no change. That means the flip-flop is not in operation in the absence of the clock pulse. So this is the truth table of the SR flip-flop. We have 4 conditions here. When both are 0, you have no change. When R is equal to 1, the flip-flop is reset and next state is equal to 0. When set is equal to 1, the flip-flop will be set. When both are 1, the condition is indeterminate. So here you can see the logic symbol of the SR flip-flop. So it involves the S and R as inputs and Q, the output and complement of the output at the output side with the clock pulse given here. So, and the next one is the input and output waveforms. There is a general clock pulse, and this clock pulse is marked with positive edges because we are seeing about the positive edge triggered flip-flop. So that the positive edges are marked here. Only at the positive edges, the flip-flop will respond. So the values of S and R are marked. According to the values of S and R, the Q, the output of the flip-flop is also marked in the timing diagram. So next one is the characteristic equation. So in the characteristic equation, this is used to define the next state of the flip-flop. So this equation gives the next state of the flip-flop. Here the Qn plus 1 is equal to S plus R bar Qn. This is the characteristic equation. This equation is obtained by drawing the K-map with the help of the truth table. So if you draw the K-map with the SR and QN as inputs and QN plus 1 as the output, so you can get this equation. So next one is the negative edge triggered SR flip-flop. So negative edge triggering means only thing that will change is the edges, the flip-flop will respond only at the negative edges. So here in the truth table, all the clock pulses are pointing towards the downward direction. So this denotes that negative edge triggering is happening. And the remaining conditions is same. When both are 0, no change. When reset is 1, the flip-flop is reset. When set is 1, the flip-flop is set. And when both are 1, it is indeterminate. So these conditions are same. Only thing is that the flip-flop will do its operation only in the negative edges of the clock pulse. So when the clock pulse is 0, there will be no change whatever the inputs may be. So similarly, logic symbol and input output waveforms are drawn. The characteristic equation also can be obtained from the K-map, which will be the same characteristic equation will be obtained for negative edge triggering also. So this is a realization of SR using NOR gate. So instead of NAND gates, here NOR gates are used in order to demonstrate the SR flip-flop. The next one is the D flip-flop, which is also called as delay flip-flop. Delay flip-flop or data flip-flop. So this is a logic diagram using NAND gates and NOR gates also. Equivalent diagram for the data flip-flop, delay flip-flop. So coming to the truth table, delay flip-flop, here it is given as the positive edge triggered D flip-flop. So in the positive edge triggered, the clock pulse is high, that is it is pointing towards upwards. So it denotes the positive edge triggering. Here the conditions are the D flip-flop, the D is equal to the next state. Whatever the D is, delay input is, it will be equal to the next state. It does not consider about the present state. So if D is 0, the next state is also 0. If D is 1, the next state is also 1. So in the truth table, you can see that for whenever D is 0, Qn plus 1 is also 0. Whenever D is 1, Qn plus 1 is also 1. It does not consider anything about the present state. So when the clock pulse is 0, so whatever may be the D is, but the operation does not happen, so that the present state is equal to the next state. So this denotes that when clock pulse is 0, it will not function, the flip-flop will not function. So the characteristic equation is given as Qn plus 1 is equal to D. So this is also obtained from the K-map, and the logic symbol is given, and the input output waveforms timing diagrams are given. So it involves the clock pulse and D and Q waveforms. So next one is negative edge triggered D flip-flop. So in this flip-flop, in this flip-flop, the flip-flop will give its response only when the clock pulse is at its negative edges. So in the timing diagram, you can see that the outputs are the flip-flop give its response only at the negative edges. So truth table is similar to the positive edge triggered D flip-flop, and the diagram is also similar. The next one is the JK flip-flop. So as we see, the disadvantage of SR flip-flop is the output will go to the indeterminate state when S is equal to 1 and R is equal to 1. So in order to eliminate that disadvantage, we are moving on for JK flip-flop. So in the JK flip-flop, the remaining conditions will similar to the SR flip-flop. Only when J is equal to 1 and K is equal to 1, we have the condition of toggling condition. So when S equal to 1 and R equal to 1, we have indeterminate condition. So in order to overcome that, we are going on for JK flip-flop. So in the JK flip-flop, J equal to 1 and K equal to 1, the condition is toggling. So the present state is toggled. The next state is toggling of the present state. So the remaining conditions case 1, case 2 and case 3 are similar to the SR flip-flop. In the truth table, you can see that when J equal to 0, K equal to 0, similar to that of SR flip-flop, we have a no change state. And when K equal to 1, it is called as reset condition. So the output, that is the next state is 0. When J equal to 1, it is a set condition. Qn plus 1, that is the next state is 1. When both are 1, J equal to 1 and K equal to 1, you have a toggle state, that is that if the present state is 0, the next state is 1. If the present state is 1, the next state is 0. So the toggle condition will occur. Here the indeterminate condition is overcome. So this is simplified truth table for JK, and the characteristic equation is given as Qn plus 1 is equal to J Qn bar plus K bar Qn. So this is obtained from the K-map. And the input output waveforms are drawn. Since it is marked as a positive edge, the clock pulse will respond, that is the flip-flop will respond only at the positive edges of the clock pulse. So then using NAND and NOR gates, the JK flip-flop is implemented. So important condition in JK flip-flop is race around condition. So in the race around condition, when J equal to 1, K equal to 1, the output gets toggled. As we seen that it is the general condition of JK flip-flop. So output gets toggled from 0 to 1 and 1 to 0. So it is continuously toggling. So this continuous toggling will make the value of Q to be uncertain. So this is known as race around condition. Master slave SR flip-flop, and you also have master slave JK flip-flop. So in the master slave flip-flop, you have two flip-flops, one act as a master and another act as a slave. So the clock pulse of the master slave flip-flop is not edge triggered. Only if the command is given by the master, then only the slave will do its function. So in this diagram you can see that, so the master's output first it is getting set, and then only the slave will get set for the next clock pulse. So once when master reset, the slave also reset. If the master is in no change condition, the slave also is in no change condition. So when the master gives command, only by observing the master, the slave will perform its function. So this is the block diagram of master slave D flip-flop and for JK flip-flop. Then the last one is T flip-flop. T flip-flop is otherwise known as toggle flip-flop. So it is the modification of JK flip-flop. It is obtained by connecting both inputs J and K together. So T is the input which is given to the connection of both J and K inputs. So here the truth table will act like, so whenever the T is 0, that is whenever the toggle flip-flop, the input T is 0, the output will be same as the present state. Whenever the T is 1, the output will be the complement of the present state. So that is given in the simplified truth table. So here in the simplified truth table, when T is 0, Qn plus 1 is Qn. When T is 1, Qn plus 1 is Qn bar. So this is the simplified truth table of the T flip-flop, and also expanded truth table is also given. When T is 0 at both the conditions, what is happening is Qn is Qn is rewritten in the Qn plus 1. That is, there is no change in the states when t is equal to 0. When t is equal to 1, the output is the complement of the present state. So characteristic equation is given. Qn plus 1 is equal to t Qn bar plus t bar Qn.